Here's our challenge for today.
Make a series circuit.
With 1 ammeter, 1 battery, 1 capacitor, 1 bulb, and 2 wires.
Okay.
So here's all the stuff here. And 1 battery, 2 wires, 1 bulb.
And 1 capacitor?
1 capacitor.
Okay, just one of these. Okay. So, does the capacitor go in the flow?
It's a series circuit, one thing after another.
Oh, yeah, okay. Let's go ahead and do it like this. So, one ammeter. Oh, let me just put the ammeter in first here so I can. I'll put this one. Okay. Come on. This guy, he makes just like inventions that are like ridiculous. He copies Crocs a lot of times, but he calls them gators. And so I was just thinking about this alligator clip and how it's a gator clip. Inner battery capacitor, 1 bulb, and 2 wires. Okay. So we've got current. Oh, the current went all the way down to 0.
Huh. Okay. Now hold on a second. Where is the mouse?
So,
Question. Why does the current stop?
oh, so it must be being stored in the capacitor or something?
Well, why did the current stop?
Because there's too much resistance?
Well,
No, because the flow must have stopped.
that's, well, obvious.
There must be
Yes,
something
you're right.
stopping it, blocking it.
Okay, so the question is, what is the capacitor?
And so the capacitor stores the charge.
Well, that's
Stores
what a
electric-
capacitor does, but that's not what a capacitor is.
Oh, what is it? So it's two plates
Yeah.
across from each other, and the electrons, move from one side to the other.
So let's go get our
Yeah.
pi plates. Pi plate capacitor.
What is the capacitor?
Can electrons get across between the 2 plates? Can they?
Say it again. Oh, can they?
Can electrons get, because what you're
because
doing,
they have to be pumped across.
yeah, well, okay, so what's happening here is you had current. So where were electrons flowing when you first, let go of it.
Of this thing?
Yeah, just go ahead and take it off.
Oh, take
there.
this off here?
Yeah.
Okay.
Okay, so where were electrons going? There's the negative end right there. Okay,
Going
they
this
went through, and
way.
the bulb lit up.
Yeah, a
And-
little bit at the beginning, right? And the
Yeah.
current went like this for a little bit, and then
Okay, and so electrons, and then where did they go?
they go over here.
Okay, now, did they complete the circuit? Did they go across back to the battery?
Probably. So I think the answer is no, because
The answer is
current
no.
went back down to 0.
The current went back to 0 because what is a capacitor? It's 2 plates that are separated.
And so when we did our previous lesson on capacitors, we were pumping them across.
Yeah.
So we're not pumping. Is that,
Well,
is that
the
why?
battery's doing the work for us.
Yeah. Oh, okay.
So the
okay.
battery is pumping electrons.
Oh, okay.
And it's taking electrons from this side
Uh-huh.
and putting them on this side. So we weren't cranking it, the battery was doing the work, and so electrons were flowing.
Yeah.
It lit up the bulb and showed up on the ammeter.
Yeah.
So, but then when it stopped, that's because
Oh,
the batteries couldn't put any more electrons
that's what I was
on.
gonna say. So it reached its capacitance, right?
Yeah.
Because at some point you can't put any more electrons over there.
Right. So how is a capacitor different from a resistor?
So a resistor, current will keep flowing through it,
Yep.
whereas in a capacitor, once it reaches that threshold of the ability to pump those electrons over, it stops and it breaks the circuit.
Yep. So take the wires that were on the battery, this one and this one, and touch them together.
Oh, I must have these. It gets going in the opposite direction. Do I have these mixed up?
No, you're good. You're
Okay.
good. Did anything happen?
Yeah. So initially went this way, and now it went back to 0.
Oh.
Okay.
Oh. So do it again. Put this on the positive side, and
Oh, I see it. Okay. Cool.
okay, now take it off and touch it to
Oh.
So what's the ammeter telling us?
So usually, when that's happened in the past, it's because we wired it wrong. But what I think that really means is that they're going back that way. No,
Well,
the current is negative.
So when you hooked it up, the current went this way.
Oh.
And then
it's because the
when
current's
you,
going the opposite direction.
yeah.
Okay. So even though it's conventional current, we're going to talk about current in the way that we
Yeah.
were talking about. So
Electrons
current
are
was
flowing.
going. Yeah, electrons were flowing this
And
way.
why would they do that? What's going on inside the capacitor?
They're being moved from here to here.
Yeah, and there's repulsion from each other
Mm-hmm.
and attraction to the naked protons, and you give them a path to flow back to where they were.
Yeah. Okay. That makes sense. Wait. Actually, I lost it for a second. Say that one more time.
Okay, so first hook it back up.
So right here. So at this point, they're flowing right here, and they're being pumped from from one side to the other.
Yeah, and then disconnect it. Okay, now what's the situation here? Now you've got what's going on inside the capacitor.
At this point, the I don't know I get confused on how to look at the sides, but
Well, I'll tell you what, it's charged. The capacitor is charged.
Yeah.
What does that
There's
mean?
a potential difference,
Yeah, there is.
between the two plates.
What does charged mean?
It means that there's a positive or negative charge.
On one side and a negative charge on the other side.
Yeah.
Okay, and then go ahead and touch them together.
Yep.
And now what's happening?
So that's the part I get confused on. So before we were pumping electrons over here, it reaches its capacity. Now they're going back.
Okay, so what you've got is a bunch of negative electrons here and a bunch of naked protons here, and they're separated. They can't get back together. And
When I touch here.
and when you touch there, that's like providing a path. When we took the screwdriver and touched like that,
Okay. It's less important about it's less important to understand which direction they're going, and more important to understand what's happening, right? And it's just a path that allows them to flow back.
I agree.
Right,
However,
okay.
it is non-trivial to talk about which way the electrons are going. Okay,
It's
because
non-trivial.
non-trivial. It is important. So electrons
Okay.
leave the negative. They go through the bulb. They go through the ammeter, and they go in here. Electrons are pulled from here. So for every electron that gets pulled out, one gets put in.
Yeah.
So what happens, you get a bunch of electrons on this side, and this side's missing a bunch of electrons. So this side's negative,
okay.
this side is positive.
I got it.
So you
okay.
have charge stored in that capacitor.
Yeah, this side becomes more negative, this side becomes more positive.
Yeah.
Is that right?
Yeah.
Yeah.
And we'll see that in just a
I
minute.
guess I was confused because this side the current is flowing this way, the electrons are flowing this way, but this side is getting more positive. It was
Yep.
just kind of backwards. Okay.
All right, this time, let's put a voltmeter on the capacitor. Let's put the red over here and the black over here.
Okay.
Okay, and go ahead and hook it up.
Okay. So no current flowing, but it's storing the charge.
So now we've got an electrical potential difference. Now there's charge stored in here, and we have an electrical potential difference.
About
Now-
1.5.
Yeah, now take it off and touch them together again.
Let me go. Here we go. Okay. So that makes sense. So now now it's being reduced to 0, which means there's no more charge being stored, which means there's no difference in.
No electrical potential difference between the two plates.
Yeah, that makes sense.
Okay? All right. Okay, so now go ahead and let's charge up go ahead and hook it back up.
Okay.
All right, so it's fully charged now. Now take the voltmeter leads off of there and put them across the bulb.
Okay. Really?
You don't have to hook them on, just touch them. Nothing.
Huh.
Nothing.
So that makes sense because this is a 1.5 volt battery. It's literally all going to this thing.
Yeah. Well, and so now you don't have to bite them on. All you have to do is
Touch them on there.
touch the black one. Now do it across the battery.
Yep. And there we have
So we've got that, and then
one half.
just touch them to the capacitor.
one more time.
Yeah.
Okay, so here we go. Yep, 1.5 there.
All right.
So that's interesting. So how come it like prefers the capacitor over this? It just probably has to do with the resistance of the bulb, right?
Okay, well, prefer the capacitor. Well, right now, is there any current flowing?
No, there's no
There's
current.
no current flowing. And so if there's no current flowing through the circuit, that's because this is charged up. There's no current flowing through this.
Oh, because in the beginning it does light up a little bit. You're
It
right,
does
right.
light up a little bit at the start. So
Yeah.
there, in fact, we could try that. Yeah, go ahead and touch them together. And let's put the black one and the red one here.
We will link them on for real this time. Okay.
And then go ahead and, okay, so it went up to about half a volt, and then it went back down to 0. Okay, it went back down to 0 because there's no current flow.
Yeah. So it was doing its thing, and then
Yeah. When current's flowing, there's a potential difference because the bulb is converting
I
electrical
mean, it
energy
halts.
into.
So you have to like,
Yeah.
Okay, and then I go. Yeah. Okay.
All right. Okay, so let's make a diagram of the circuit.
Okay. So we've got battery. We've got bulb. We've got, and then where do you want me to draw the voltmeter?
Well, it's the ammeter.
Oh yeah.
Yeah.
And
then what's the symbol for a capacitor?
I can't remember.
I'm taking this off.
I know it's so hard to talk with that thing on. Oh, that's right.
I think.
That's right.
Hi.
When I talk all day, I get out of breath.
Okay, so now, can you see why? If you look at the diagram, can you see why the current stops?
Yeah.
Because it's like an open switch.
Yeah, it's literally. Gotta make sure your battery and capacitor.
All right,
looks
so
like
let's put the voltages we measured. On the battery, it was
that.
what, 1.5?
volts. Let me do. Did you bring me different colors so I could do different colors on here? Is that the idea?
Well, whatever you like. I know that you're
Colorfully
you're
inclined.
artistic bent.
Okay, 1.5 volts.
And if you want to check it again, we can.
Yeah, the volt. This was about 0.5 volts, right? Well,
No, I would leave that alone. No, once it was fully charged, it was 0.
yeah, this is 1.5 volts when we were done with it. Okay.
And write charged on the top there.
Like right here.
Wherever.
Charged.
So this is a charged situation. And the ammeter read 0, and the voltmeter read 0. 0 amps and 0 volts.
Sorry, let me do that. And
So the ammeter read 0 amps, and the voltmeter across the bulb was 0.
0, yeah. Okay.
Now, let's throw another battery in.
Wait, is it like this, right, William?
Negative to the spring.
Negative spring.
And then you'll have to bite it to that, so.
Okay, so it says charge it, do it, make it happen. Okay, so it really ramps up a lot more this time. I did not look at the thing.
Okay, so the ammeter went much higher this time.
Yeah.
The current was higher. Okay, now measure the voltage across the
I would assume.
3 volts.
Yep.
3 volts, which is what you'd expect.
Yeah.
Because you've got 3 volts on the
What else
battery.
there?
Okay, now touch them together again. See what happens.
And so what I'm seeing is it same exact thing, but it holds for longer because there's more current that's been stored.
Okay, there's more charge
More
that's been
charge.
stored because what happens is as you take away more electrons from one plate and put more electrons on the other, they say, you ain't getting no more.
Yeah.
Well, you say, oh yeah, well I got me another battery, I can do some more weight on you, so it can pull out more.
Yeah.
So there's more charge.
Okay.
All right.
Should I do you want me to do this or no?
Capacitance is defined as how much charge 1 volt can put on a capacitor. And the unit of capacitance is the farad, named after Michael Faraday. So,
Do you want to hold the camera for your blanket?
C is equal to Q over E. Okay?
Okay.
Okay. So, use the label capacitance. Calculate how much charge is stored on the capacitor for 1 and 2 batteries. So this is 100,000 microfarads. That's 0.1 farad. So C is Q over V. If you want to solve for Q, that's going to be CV.
Equals CV. Mm-hmm.
So this is the C is 0.1.
And farad is F or
F, yes.
F, right? Okay. Okay.
And
times
we
the
had
voltage.
1.5 volts.
Okay.
Need a calculator. Well, actually, you don't need a calculator. Because it's 0.1 times 1.5 is going to be 0.15, right?
Is that right? 0.15.
Yeah.
So 0.15
Coulombs. So there was 0.15 coulombs of charge in the capacitor when you had 1 battery.
Coulombs per volt. Okay, that makes sense. Okay. And then here it's just going to be 0.3.
Yeah. 0.3 coulombs. So you had twice as much charge stored in that capacitor. And you can see that's coulombs per volt. So how many coulombs per volt? And that's what this is.
Yeah.
That's 0.1 coulomb for every volt. So you had 1.5 volts, 1.15 coulombs.
Okay, that makes sense.
So that's
That's how much charge was stored
Yeah.
on that when they pumped it
in a
across.
capacitor. Okay.
Oh, wow. It's not capacitor in parallel with the first. Okay. Okay, so then just
What you
put
can
it-
do is just put this right here.
Yeah, right. And then
And go across.
I clamp like this, right? I put it right here.
Yeah.
To the negative one. Oops. And then over here. To the positive one. Okay. So, and this is the same size capacitance. Okay, 2 batteries?
2 batteries. And
Okay.
let's see what happens.
Batteries, okay. And here we go. Okay, so it jolted again, but it seems to be taking longer
A longer time.
to go back down to 0 for the current. Okay.
Okay, so it took a lot longer to do that with 2 capacitors in parallel. Why do you think that is?
More time. It took. There's twice as many places to store that.
What's
the
happening
coulomb.
every second in the wires?
Electrons are flowing.
That's right.
Charge is flowing.
So if the electrons are flowing for a longer time, that means
It's just going to take longer for those places to charge.
that means you're getting more electrons on there.
Yeah. Yes. Yeah.
I move the. Let's see. Where's the?
Where is it? There it is. Get there. What was different? What was the same between a single capacitor and 2 in parallel? Why? Oh, I think we kind of just answered this. So, the same was the amount of current that was that it had access to that it read.
Okay.
But what was different was how much time it took to fall back to 0, because there's wait, what did we talk about? Every what's being carried in the wires, electrons, and now we have 2 different places to store the electrons. There's
Yep.
more electrons to store. It takes longer to.
That's exactly right.
Yeah. Okay. It's not. What is it called? This is not discharge, because now they're charged. What is it called when it goes to 0?
Well, what is an ammeter measuring?
Electrons.
It's
per
the
second.
rate of electron flow. It's current.
Oh, okay.
So now let's discharge.
Oh, and look at that. We had a little bit of
It
light
stays
that time.
there. It stays there. It stays
Yeah,
there.
it's still staying.
So So that's a much longer time to
And because
discharge.
there was more time, and the circuit was completed, this now had the opportunity to light up. Because I don't
Yeah.
think this lit up the other ones. I would have noticed it.
Yeah, yeah.
So,
Okay, so what I'm going to do here.
so that's what we have right now. Should I add in our stuff right here?
Well,
Or do we have we don't have anything to add in. We didn't take the measurements.
okay, now why? So if you can get twice as much charge on there, and you can see why, right? It's like effectively you're doubling the size of the plates.
They each have access to the battery. It's just like when you're in parallel,
Yeah.
and it has the voltage is the same across both parallel.
And if you just have one, you charge it for a while till it's full, it can't take anymore. But when you have two, you can get twice as much charge on there. Does that make sense?
That makes sense.
All right.
It's like you're doubling, like I said.
Yep.
Okay. What's next? Make a diagram of the circuit and label the voltage.
Okay, we haven't.
measured.
Here's another one if you want.
So it'll look like these. So we've got our battery, or our bulb over here, our ammeter here, and then we'll go ahead and put our capacitor here. Like that, right?
All right, so let's charge it up again.
Now we got 3 volts, right here. All right, and then I need to put this over.
Well, no, just go ahead and charge it.
Oh, okay.
Just hook it up. And you could definitely see the bulb light up when you did it.
I wasn't even looking at it.
Yeah, well, I did it. I had it in the
Okay.
camera. Okay, now take the voltmeter and
Put it across both elements.
yeah, just touch it.
Yep, and we've got 3
3
there.
volts.
3 volts
3
there.
volts here, and what's across the
Da-da-da-da-da-da.
bulb? You got
0.
Nothing. And across the batteries. 3 volts.
3 volts. There we go.
Now just unhook it, and let's just confirm that we still have
3 volts.
voltage.
Oh, that's a good idea. Bada boom. Yep.
It's still there,
How cool.
and it's still there.
Uh-huh.
All right, and so now go ahead and discharge it. Yeah.
3 volts. 3 volts and charged. 0 volts. Like that.
All right, and then go ahead and discharge it. We'll watch the bulb this time.
Cool.
All right, capacitors are cool.
There's the thing. 0 amps.
Okay, here's just the definition of capacitance solved for all 3 variables.
Yep.
Quantity of charge is the capacitance times the volts, and the volts is the amount of charge divided by the capacitance. It's a simple thing.
Which one do you like? You know how you just think about an equation and that's your go-to and you do all your math in that one?
But the C is Q over V.
C is Q over V, okay.
That's a definite, it's how much charge per volt.
Yeah.
And the units, like always, they tell you.
Yeah.
All right, so capacitors in parallel, the voltage is the same across both capacitors. So the total voltage is on the voltage across one capacitor, which is the same as the voltage across 2 capacitors. And however many you have in parallel, the voltage is always going to be the same
Yeah.
when they're in parallel. Just like with parallel resistors or parallel light bulbs. That's all right.
Yeah.
And the quantity of charge adds. The total quantity of charge is the quantity on one plus the quantity on the other. Okay, and notice how this makes sense? I hope.
Yeah. It's the same as before. Same rules. Junction rule.
And capacitors in parallel add together.
Okay.
So the total capacitance is the capacitance of 1 plus the capacitance of 2.
Oh, so
So we got 0.1 plus
Yeah.
0.1. The total capacitance is 0.2.
Okay.
All right, and we had before, and it's going to be twice as much.
2 times as much as when we started. Okay.
Yeah. So you got the
So-
total capacity is 0.2.
So basically, from everything that we've done before, we could also calculate the capacitance for everything we've done in the past, basically.
Yes, we could.
If we were to put
Yeah.
a capacitor.
If we
in
know
it.
the voltage and we know the quantity of charge, we could. And well, if we knew the capacitance,
Yeah.
you know, it's hard to know the quantity of charge.
Yeah. Why are the capacitors together in series? Connect to the batteries and charge. What is the difference? So I was just thinking about this as you were talking about it. So
Now you go ahead and leave the
sorry,
bulb
yeah.
there. All you're going to do is change the capacitors.
So if we said in parallel, they add together, just like with the voltage. So
Yeah.
that, you know, these receive equal amounts of voltage, 3 volts each. So they each can hold 3 volts each. And their
Yeah.
capacitance they add together. So what will happen here? Okay, so first you'll see what happens. Okay.
All right, notice what happens. You got 2 batteries, 2
Mm-hmm.
capacitors, and what did you notice about the current?
It went to 0 significantly faster than last time we had 2 capacitors.
Okay, so, and now let's discharge it and see what happens.
And quicker than in parallel.
So,
for sure.
what does that suggest if if it charges up much faster?
It suggests that the electrons are being pumped or moved from one side faster.
Yeah.
Not as many,
Yeah.
right?
All right, so let's take a look then. I'm gonna, let's see, you got da. All right, good.
Can it even use the second capacitor?
Okay, that's a terrible drawing. Okay, so what's different here?
So because they're in series, I mean, I see one gap, and then I don't know how the electrons.
So here's a gap here,
Yeah.
here's a gap here, and an interesting question comes out, which I have conveniently asked here.
Oh, we did that. Compare it with the 2 caps in series. Discharge the capacitors, hook up a single capacitor.
I know what it is. It's different.
We did that.
All right. So we've got a diagram up here.
Yeah.
Let me get another.
Oh, the whiteboard?
Let's make a diagram of 2 caps in series.
Okay, so we've got. My drawings have gotten worse and worse.
It all depends on the time you're taking.
Yeah. Okay, so here we are.
All right, so let's charge it up and measure the voltages.
3 volts here, right?
Yeah.
Okay, so I can recharge it up like this.
Yep. And leave it hooked up.
Bada boom. Okay, so the first one, we'll go ahead over here. So we've got
1.5 volts.
1.5 volts, okay. And then over here, 1.5 volts. Okay, so out of 3 volts.
All right, so mark that down on your thing. And notice that this is very similar to a series circuit of resistors,
Yeah.
where the resistors have to share the voltage. The capacitors have to share the voltage as well.
Yeah, and in this case, it's the same because their capacitance is the same.
All right, so
Okay.
let's calculate the quantity of charge in one capacitor.
Okay.
It's
so,
0.1.
So charge is equal. So the Q is
QV,
C equals Q over V.
Q over V.
Okay, and what were you wanting to calculate? You said the...
Well, no, we have the capacitance. It's 0.1. We want to calculate
charge.
Q.
Which equals 0.1 farads times the voltage was 1.5, which is going to be 0.15 again?
0.15. So that's what we got before
Yeah.
when we had just one capacitor. So what we've got is, we've got two capacitors, but you've got 0.15 in this and 0.15 in this. So each capacitor has less on it. All right, and I think the good question comes up here. Notice that the total voltage is shared between the capacitors. We just talked about that.
Shared,
All right.
Before Boykin,
Yeah.
this 0.3 coulombs, that was when we were in parallel like
That was
this.
when we were in parallel.
And, okay, and they both saw 3 point, okay, yep, okay.
All right, so notice in your diagram, the two plates are not connected to the battery.
So I'm assuming that this one gets charged first and then that one then.
Well,
Or what happens on these plates?
okay, so here's the negative side. So here's the positive side. This pulls one electron from over here and puts one electron over here. Okay, so that means that this plate on the outside is negative and this plate on the outside is positive.
Wait, can you draw that? Here, watch this.
So this is the positive side. Electrons come this way, makes this side positive. The electrons go this way, makes this side negative.
So this is the part that this is what I needed to see. Okay, because I was thinking, boy,
Check this out.
Okay.
Okay, well, what happens here? You've got electrons in this that are going to be repelled from this, and they'll be attracted to this. So electrons will go over here, making this positive and this negative.
Oh.
And why are electrons going over here? Naked protons, they're attracted to this. Why are electrons leaving over here? So inside, even though there's no there is no contact with the battery.
You still have a pulse and attraction forces driving stuff.
Yeah.
So wait, let me see if I can explain that. Here, hold this real quick. So we said that this is the negative side of the negative side of the battery, positive side of the battery.
Yep.
And what happens is we pump our electrons over here.
Yep.
Right. So we've got
That
electrons.
outside plate becomes negative.
Okay. So so that's becoming negative, and we have protons. Sorry, what did you say after
Yep,
this?
you're right. No, protons,
here?
positive, because the positive side pulls electrons away, making that positive.
Oh, I see. Okay, so
The outside plates, the one on the left is negative, the one on the right is positive.
like negative like this.
Yeah, and electrons are going from this plate to that plate.
Oh, okay, making it positive. So electrons are running away from here and going here.
Yep.
And these negative charges right here are
They're stuck
scaring.
there.
They're stuck there, and they're scaring the electrons that are here
Yep.
over here,
Yep.
making this positive. And in turn, these electrons right here scare these ones away.
Yeah.
And also, these electrons are also doubly attracted over here to this
Yeah.
positive side.
And so what you've got is 1.5 volts here, 1.5 volts here. Now, how can you have a potential difference if both sides are charged? How does this side become charged? Because of the connection, and you should draw that line
Oh,
in.
yeah.
Because the connection between those. Yeah, that's good.
Okay. Okay, that makes sense. Okay, so coming back over here,
Yeah.
just so I think that I was not understanding completely it's just like the direction of what's happening. Actually, let's just do one capacitor. Okay, so pretend like we've got this going on right here.
Yeah.
So we turn on the current, and it says the current is there, and we've got our light bulb and our ammeter, and then it goes back down to 0.
Yeah.
And at that point, electrons have traveled here to this side over here.
Yep.
And so electrons are here.
Yep.
Okay, but the battery has pushed them over here, right?
Okay, what happens is electrons have left here and they're attracted to the positive. So this side becomes positive.
Okay, so there's current, current is flowing through it, and at some point, all the electrons that have been put over here, this is why it's kind of like confusing. So electrons are traveling through, and doing their thing. They're attracted over here, and at some point, those electrons
Now
stop.
hold up. This is the positive side, right?
Yeah.
This is the positive side. So it pulls electrons off. This side becomes positive because it's missing protons.
Yeah.
Where do those electrons go? They go on the other side. This is the negative side over here.
And once these have reached their max, that's when it stops.
Yeah.
That's when it.
Well, what happens is the battery's got only so much.
Yeah.
Okay, and so
Okay, that
after
makes
a while, you got negatives over here. You're trying to take positives away, and they go, and you're trying to make it more, I beg your pardon, you're trying to take more electrons away from this side, and they're attracted to the naked protons. And over here, you're trying to shove more electrons in, and it's already full. It says, get the hell out of here.
Yeah, okay.
And the battery can't shove any more they can't take any more, they can't put, it's like a saturated situation.
The battery is doing the work to pump the electrons
Yes.
through our circuit here.
But it can only do so much work.
It can only do so much work, and as you pump it through, our protons are building up on this side, and our electrons are going through to this side.
And think about what happened when we went to 2 batteries.
We were able to do.
When you had 2 batteries,
more.
you could take more away, so you got more positive,
Yeah.
and you could put more in. And as we calculated, you had twice as much charge stored when you had 2
Yeah.
batteries.
Yeah, if I was a student, the story of what happens here would be something that I would need to really nail down.
Okay, now like everything else in physics, the idea isn't hard, it's just alien.
Yeah.
You have no experience with this. And that's something I have to remind myself, and we have to remind our students. This doesn't make sense at first. Why? It's not because it's hard, it's not because it's impossible, it's because you never seen it before.
And when I first was thinking about the capacitor, what I was thinking, and it's hard because again, I'm just like I'm capacitors are like I get them, but then I have second thoughts about them.
Yeah.
But I was thinking that the action was all happening right here, I was thinking that these are being pumped across here, but they're not being pumped across here.
Nope, they
That's
don't.
the biggest
There's nothing
misconception.
between. In fact, there's an insulator between them.
Yeah. So it's not that the electrons are being pumped across this. Rather, it's that nothing is happening here, and the electrons are being moved around and put onto this side of the plate.
Yeah. Now there's 2 things going on. There's an electric field in between.
Yes.
So these electrons feel a force of these, and so they're attracted to this, but they're also repelled from each other. So there's 2 things going on at once. There's an electric field stored in here, and so when the current starts, that's where we're getting the potential difference. There's an electric field. The energy that the battery did was stored in the field. And what is that field? Well, it's the combination of forces, attraction between all of these and all of these.
And then when we touch that thing back there and we connect it, now it's going this way.
You're making a short circuit. Yeah, you take the battery out of the equation. The batteries don't, because why do they stay here? Because the battery is holding them.
When you discharge, what happens there?
Basically, you take the battery out and you connect the 2 wires together, and now there's a conductor that goes from one side to the other.
Wait, you're not these 2
Draw a
wires?
line from here to here.
From here to here.
All right, and you take the battery out. Now you've got electrons can get back to the other
Oh,
side.
I see. Okay, because I'm like the battery's done all it's maxed out.
Yeah.
So okay. It's making more sense. The concept makes sense to me.
Yeah.
So it's just the nitty-gritty descriptions. So.
All right. For caps and series, the same amount of charge is on every plate. Same amount of charge is on every plate. Okay, so for every electron you take away from here, that's how many electrons are on here. And for every electron that gets attracted over here to this side, there's an electron missing. And so the charge on this negative is equal to the charge on this positive. And the charge on this negative is equal to the charge on this positive. And we could find that out. We had 0.1 capacitors, and they had 1.5 volts.
Yep.
So this had 0.15 coulombs on one, 0.15 coulombs on the other.
Yeah.
So they have the same quantity of charge on both plates.
Okay. Capacitors in series.
The total capacitance for a series, and notice how this is different from
It's
resistors.
opposite resistor.
Yeah. So it's an inverse relationship.
Which kind of makes sense because if you think about, like you said, the capacitors in parallel, it's like you have double the, you know.
Well, right. Well, and what you have is you have 3 volts. And when you have one capacitor, 3 volts for 0.1, you get 0.3 coulombs of charge on this. For 3 volts with 2 of them in series,
Yeah.
you get
1.1.
0.15 and 0.15.
Yeah. So it has to share them.
Yeah. So basically what this means is you got 0.15, let's see, that's a tenth plus a tenth.
You said 0.15 -1, right?
Yeah, you got
0.15 plus, oops, 0.15, and then take that to -1, so I get 0.075, so like 0.1.
yeah.
That makes sense, it's less than 0.15. 0.1.
It doesn't sound right to me. Okay, you got point. Here, you did the. Let me see.
Yeah.
You got point x, 0.15. Yeah, 0.075. That is 0.075 is not half of 0.1. Yeah, it's more than 0.1.
No, 0.075 is less than 0.1.
Yeah.
Yeah.
Yeah. So you get less resistance, I beg your
yeah.
pardon, less capacitance in series. So it's just the opposite of. Okay, what's the same
Of
about
resistance.
caps in series and resistors in series?
What is the same about caps in series and resistors in series? Oh, they are both there. So they both. If you put resistors, wait, hold on. What is the same about capacitors in series and resistors in series? So resistors in series increase the resistance.
Okay, that's what's different about them. Okay, so let's take a look at the diagram here.
Yeah.
What's this? If these are resistors instead of capacitors, what would be the same?
The current.
Mm,
I'm sorry. Wait.
Be the voltage drop, wouldn't it? Because
Wait. Say your question again one more time.
what's the same about capacitors in series and resistors in series? They share the voltage.
They share. Okay. Yeah. They share the voltage.
That's it.
Oh. Okay. So they share the voltage. Okay.
So they share the voltage.
Okay.
And
Yep. That makes sense.
okay. And what's different about caps in series and resistors in series?
It has to. It's the relationship of the 1 over.
Yes.
How do I describe that?
Resistors add
Resistance.
Capacitors.
Capacitors.
More resistors, more resistance.
Yeah.
More capacitors, less capacitance.
Yeah. Okay. More resistors, more resistance, less capacitor, less capacitance.
Yep.
Okay.
More capacitors, less capacitance.
Oh, sorry. Yeah, because it's the inverse relationship there.
Yep.
Okay, that makes sense.
All right. What's the same about caps in parallel? Here's our parallel right here.
Yeah, so caps in parallel, they both have equal access to the voltage. That's what's the same about them.
Yep.
Right? So instead of over here where they share, which is similar, they have equal. They have
And that's
equal access.
that's a function of parallel and series circuits.
Yeah.
Is the voltage is either shared in series or equal in parallel.
Yeah.
Okay.
And then over here, when you add more resistors, the resistance decreases.
Yep.
Over here, when you add more capacitor, the capacitance increases over here for this one. And
that's it.
yeah. Okay.
Now, and that's the end of this. Yeah. Now, I want to tell you
That was the part that when I was like thinking, when we were going through, I was like, I cannot keep this straight. Then it's they're opposite when it comes to the resistance and the capacitance.
All right, now I'm going to hand you this. I'm going to
Okay.
do a quick lesson on the board.
Okay.
What determines capacitance? Well,
Is it like how far the plates are apart or something? Oh, how big the plates are. That's right, because how far apart the plate just has to do
well, no,
with
we'll
the-
get that in a second. We'll get to that in a second. Okay, here is less capacitance. Why? There's less area.
Mm-hmm.
And here you've got more capacitance. You can take more because there's more area.
Mm-hmm.
Okay, another thing is, and you touched on it, okay, now here, let's say that this is the negative side and this is the positive side. And how much force is there going to be? How much force is there going to be?
It'll be more force there
Yeah.
between those ones, less force between the further apart ones
Yeah.
because the distance between them. So
And I think what we've got
positives,
here.
positives, positives.
Thank you. I think this has to do with id.
Yes, that's what I was thinking about.
Yeah. And so the voltage divided by the distance apart equals the intensity of the electric field. So you have the same voltage on both of these. This you'll have a big electric field, and here you'll have a small electric field. So what? Well, when you're pumping electrons away from this side and onto this side, you have to do work, but the attraction here is helping the battery out. Because not only is there repulsion between these guys, but there's attraction between these guys. When they're farther apart, you get less help from the electric field.
So if there's a bigger electric field, you're gonna have it'll be is it then hold on, let me think about it.
Okay. So here you'll have very intense electric field,
Yeah, it's very intense
and here
because there's
you'll
more
have a weaker
distance.
electric field because it's now. Look at this. What's going on here? You've got more distance here. If you just have this, you got this much distance here. But now it's like you've got the same amount of area, but now they're farther apart. So here, farther apart.
I see.
This is in reality farther apart.
Yeah.
Less electric field, less capacitance.
Okay.
Now there's a third thing, and that is
More electric field, more capacitance.
should I say this? Yeah. Okay. I'll just mention it. These capacitors don't have air between them. Our pie plates have air between them, and the stuff that you put in between.
Isn't it the dialect, right?
Yes.
I was watching some videos on it. The dielectric,
Okay.
and it determines the and it affects the.
So there are three things that determine capacitance.
1, 2, 3.
Capacitance, you have, I can't remember the symbol for the dielectric. Yeah, I'll get to that in a minute. But if you have more area, you have more capacitance. If you have more distance, you have less capacitance.
That makes sense.
And then, what is the symbol for the dielectric here?
Dielectric!
I know.
We're able to find you!
Equation sound, linear superposition,
Let's get some water.
capacity.
Check out the rose gold color I chose.
It's nice, isn't it?
I'm glad I didn't go with pink. I'm not really a pink person, but sometimes I'll get pink things. So I'm like, oh, it's pink. That's kind of cool. But
Pink's a nice color.
yeah, but I don't like love it the way that's just like nice and neutral kind of.
No, it doesn't go into the dielectric here. I can't believe it's not in this book.
I thought I read about it in there. I watched a video and I was like, this isn't making sense. And then I like looked in there.
.528, 530.
We're close. Yeah.
Yeah, it's K.
That little K. Okay.
So C is K. The dielectric constant is K.
For a material.
Yeah. And then there's this epsilon sub zero, which is the permittivity of free space.
And I learned about that too. And if it's
Or is it
free
the
space,
permeability?
it's 1, right? No, I think it's permeability of free space. I didn't really understand that one as
There's
much.
two. There's permittivity and permeability.
Oh, yeah.
And one is magnetism and one is electric field.
I think permittivity is the one you're thinking of.
You know, the important thing is you understand this relationship.
Yeah, and so the capacitance increases with more area, which is what we see over here, and so the capacitance decreases with distance, and that has to do with the electric field.
Yeah.
If it's further apart, there's a smaller electric field, and that force, but that electric field force doesn't help. The electric field force helps you with the capacitance.
Right.
And then lastly, the material that the dielectric is made up of.
Yeah.
If there's nothing, it's less capacitance, but depending on what you have, it only increases it.
Yeah.
Because a vacuum it would be 1.
Yep.
And then anything else is higher than 1.
I build electronic devices and
And they're insulators, right?
they're
all
right.
insulators.
Yeah, you don't want charge.
It's the same idea as creating more space.
Yeah.
Oh, no, it's not. I apologize. Because I would say
Well, basically, what it does is it facilitates the electric field.
Oh, okay.
Okay, and it's the degree to which the material allows an electric field to pass through it. Now, the microphysics of this is very interesting, but we don't want to talk about it. But some things, for the same distance apart, you put something in there and it'll change the intensity of the electric field inside.
How come putting an insulator in there increases your electric field? Because I was thinking it would be opposite.
It changes the electric field.
It changes it
Yeah.
in such a way that's beneficial for the capacitance.
Here are some dielectric constants. Vacuum, like you said, is 1. Teflon is 2.1. And water is 80.4. That's not a very good dielectric. Okay. And, if you want to talk about the properties, the physical properties of dielectrics, it gets into it in here. This kind of...
Yeah, I was looking at this. But so if the bigger this number is, wouldn't it be the bigger, would the capacitance would be bigger, right?
Yes.
So this is this would be a good dielectric then, technically? Because it would help with capacitance?
Well, there are other situations. Let's see. And ratio of the magnitude of the electric field without the dielectric to the magnitude with it.
And that's how you determine what the K is?
Okay, so what this is saying, if you have a vacuum, the electric field without it is the same as with it. It's a vacuum. Okay, the electric field without it to the electric field with it, this is 1/80. This is 1/80th. 1/80th of what it would be if you didn't have it there.
Okay.
But here's the thing. Here we have air and styrofoam. Okay, so there's a dielectric. Styrofoam has a dielectric constant. What's inside here is two big long sheets of foil, and they have a layer of dielectric underneath them and a layer of dielectric between them, and then you roll
They
them
roll
up.
it up.
Okay, so you have to have, you can't have air, you can't have vacuum in here. You have to have some material in between these that will keep them apart.
Yeah.
Because if they touch, then it's not a capacitor anymore.
Oh, okay. Oh, okay. So okay, and then so the smaller this number is, the better then?
Yes.
Okay. That makes sense. Yeah.
Yeah, there is. Do I still have it in here? No, I think I put it in the back. I have a 1 farad capacitor.
Oh, that's a lot, huh?
It's a little. It is. It's a monster, and it's just a little button. It's about this big around. It looks like a little hockey puck.
And that's because the dielectric in there
Is because of the dielectric.
Yeah, because it's not like the distance. Well, the distance could be different, but the area is not. What were you gonna say? You said you work on electrical stuff.
Oh, and there are the capacitors that I use in these electrical circuits. Some of the old capacitors are paper that are saturated with oil. So instead of plastic, they have paper that's saturated with oil, and you roll them up. Well, what happens over time is they dry out, and then they fail. That's a bad.
That's not good.
All right,
Okay.
so we're done.
Okay, so in short, understanding this relationship here. So in a series, well, we got our equation of a capacitance is the charge, how much 1 volt, the charge that how much charge 1 volt can do work on. Is that right?
Capacitance is coulombs per volt.
Coulombs per volt. And in a series circuit, when we have capacitors in there, what's the same is that they have to share the voltage of the battery. And then as opposed to in parallel, we know that one thing that's the same is that both capacitors will see the same voltage of whatever the voltage of the battery. But this one has to share the voltage. Now, what's different is that in a series, if you add more resistors, you increase the resistance. However, when you add more capacitors, you actually decrease capacitance. Okay, kind of because you're essentially, it's like you're increasing the distance here between them. And then in parallel, if you so what's usually what happens is if you add resistance, so you add resistors, you decrease the resistance. But what you see with capacitance, because they each have equal access to the battery, it's kind of like you're making the capacitor have more area. You increase capacitance with more capacitors. And then if you when you add a dielectric, it also increases, depending on it increases the capacitance. Yeah?
Test, and on it there's this.
Okay, so original test that we were going to give the kids, and on it is this. Now we didn't include
We didn't give this to kids because we haven't taught them that.
We haven't talked about
But
capacitance.
I just taught you this.
All right, let's do it. Okay. Okay, don't go too fast. Take it slow. Take it slow here.
Okay, so I want to reduce this to 1 capacitance. What should I do first?
Okay, let me see where the capacitor. Oh, so it's all capacitors. Okay. Yeah. So first let's get rid of the one that's in parallel over there. So we know that capacitors in parallel, they increase the capacitance. So we want to add them, right?
Okay,
so we would do
parallel.
So we do 3 plus 1.
This is 4 farads.
And
this is 6.
And then now we do our 1. Now we do our 1 over stuff. Okay, hello.
Hello.
Okay, so 6 negative 1 plus. Hey, Kurt.
What are you doing here?
Why don't you just come back?
He comes back every day. 2.4.
1
Yep.
over 6 farads plus 1 over 4 farads, and you say it's what?
2.4. Well,
2.4.
once you take the inverse of that.
Farads.
That's the final.
Okay, so 2.4 farads.
So what are we finding?
Well, let's find what the voltage is across this.
Okay, so our...
Let's see, our capacitance is Q over V.
So,
Oh, wait a minute. We're going to need to know the quantity of charge stored total.
okay, so we just do
So that's going to be CV
capacitance times the voltage. So 2.4 times 5?
times 5 volts.
12.
12?
12. Mm-hmm.
Exactly?
Mm-hmm. Exactly.
So we got 12 coulombs here.
Mm-hmm.
So there's 12 coulombs.
Being can be stored right
Okay,
there.
now what do we know about the charge stored on series
It
capacitors?
has to be shared.
It is shared, but it's the same amount.
Yes, like I thought it was so before we got 0.15 and 0.15, right?
Okay, now we're talking volts here.
Okay.
We're talking volts, but let's talk about charge. If you got 12.5 coulombs, you got 12.5.
Oh, it's the same
coulombs
because
on the outer
current.
plates.
Oh.
You got 12.5 coulombs stored here.
Yeah.
How many coulombs is going to be here?
12.
12. So we got 12.5 Q. So Q here is 12.5 coulombs.
Now-
and Q here is 12.5 coulombs. This is the properties of capacitors.
So it's not related to current. That's not.
There is no current.
There's
flow.
no current. Okay.
Aha! Drop the
And there she goes.
It survived. All right. So remember over here, you've got the same amount of charge on one side as the other. So that the total capacitance on the total quantity of charge that you would have on one is on both of these.
Got it. Okay, that makes sense.
Now I'm thinking I'm not screwing up here, am I? You didn't staple these together. I was sitting.
No, yeah, sorry.
No, it's good.
No, this is. Oh yeah.
So capacitors in series. Yep, the quantity of charge total is the quantity of one, so they share it. All right, so now.
And you said that before. You talked about if one electron goes here, it goes over there too.
So we got. So we got 12 coulombs of charge here, 12 coulombs of charge here. All right. So
I got the capacitance.
now we want to know what the voltage drop across these are.
So now we just do the charge,
So
which
that's
is
just
Q.
the Boykin flip, right?
Yeah, the Boykin flip.
Voltage is Q over C. So the quantity of charge is 12 over 6.
Yeah.
And
2.
12 over 4. So this is 2 volts. And this is 3 volts.
Yeah.
2 plus 3 is 5.
Yeah. Would you put the V in there so I can't
Yes,
keep
ma'am.
track of it all? Okay. So the first thing we did was we found the charge through everything, just like how we normally find the current, we find the charge. And then again, we go back and find the voltage. And it's important to note that the charge for things in series, the charge is going to be equal on both sides. And you know what? It just reminds me, even though it's different than current, it reminds me of current because the current through series is the same. The charge is the same.
And there are things that are the same. There are the things that are different. Okay, so now on this, we know that this is
2 volts. Mm-hmm.
And we know that this is 3 volts, and this is 3 volts, and this is
12 coulombs.
12
right?
coulombs. All right, but now we've got a parallel circuit here. And we know that the total charge is 12 coulombs. That's the total charge. So where's our parallel here?
I erased it.
That's cool. So what was the thing? So what we wanted, we got the voltage, we got the capacitance. The question is, what about the quantity of charge stored? Okay, the total quantity.
They add up together.
They add up together.
That makes sense. Just like when, they have to equal 12.
So we've got the volts, we've got the farads.
So we could just divide again.
Well, so if we want to know Q here,
Oh, sorry, we
that's
multiply.
going to be CV.
Yeah. So
Q is
3
CV,
times 1.
Q is CV. That's going to be 3 times 3. This is 9 coulombs. And this is
3
3
times 1.
times 1. is 3 coulombs.
And it adds up to 12. That's what we like to
3
see.
coulombs.
Okay.
And so boom, boom, boom.
And that's everything, right?
Yep.
Thank you.
Ladies and gentlemen, there it is.
No, seriously, thank you, because I'm studying this for ham radio.
Yeah.
Yeah, and that's.
Can I stop recording, Boykin?
Yeah.
Was that everything? Okay.